Hi 242. This is going to be our video on section 15.2, which is talking about what are called partial derivatives. So we're still going to be talking about taking derivatives, but here what we're going to do is we're going to start thinking about how we can take derivatives of these functions of several variables that we've been talking about and working with in section 15.1. So in order to motivate why we would think about doing this, let's consider an example first. So consider the following cost function. This c of x equals 200 plus 30x here. If I have this cost function, say it represents the cost to produce x number of some kind of a product. Well, I can think about the derivative here, c prime of x, which is 30. And this derivative is called the marginal cost. And it represents what? How the cost changes as x changes. So if x were to increase by 1, the cost would increase by $30. Okay, well, trying to generalize that now to the situation where perhaps we're producing more than one product. Maybe we're producing two products. And we would like to know, how does the cost change as I now change the number of products that I'm producing? Well, let's consider a new cost function. Let's consider this new cost function c of xy. I'm producing two products. I'm going to produce x of product A and y of product B. And capital C, this function, would tell me then the total cost to produce those two products. Notice here that it's of a certain form, right? Just like the other one was. There's some sort of fixed cost. That $1,000 is a fixed cost. So much per unit for the producing X quantity, so much per unit for producing Y quantity, product A and product B. So if we think similarly to what we were thinking about over here, if I were to increase the number of product A that I'm producing, which is described by X here, if I were to increase this by 1 unit, the cost is then going to increase by $24. Alternatively, if I wanted to increase the production of product B by 1 unit, the cost would increase by $19. I'd like to have some sort of way to write that. And I can't just carry across this notation here because it would be really confusing if I write something like this. That's confusing. I'm saying the same notation to say two different things. So what we have to do is modify our notation here. Well, this 24 right here, the 24 that came from saying that's how much the cost will change if x increases by 1. Well, instead of using a little tick mark, how about we use notation that gives reference to the x is the thing that's changing? Okay, so we take this notation and instead of using a little tick mark for the derivative, I write a little sub x here. And that now denotes how cost will change as x increases by 1 unit. The cost would go up by $24. The same thing can be done for this other derivative, because it's sort of a derivative. It's how the function changes as an input changes. So I can't use the tick mark here, but remember that this 19 was in reference to how much the cost would change as y changed. Right? If we increase the production of B by 1 unit, if we change y by 1, the cost would increase by 19. Okay, so we give reference to the fact that the y is the thing changing here, and I put a little subscript y there to denote that. These two are very similar to what's going on in this first situation here. This first one, in this c prime of x situation here, this is the derivative of a function of a single variable, so we can use that little prime notation. These are derivatives of a function of several variables, and we've had to, again, use some different notation here to denote what was the variable that was in fact changing, since we now have more than one of them. So these are what are called partial derivatives. Okay? And we find partial derivatives by simply noticing the notation about who we're being told is the variable that's changing, and then any other variable that exists in that expression is just considered a number. So if I was given this function capital C and I said, I want to find the derivative with respect to x as x is changing, I then just have to look through the function and find all of the x's and consider those variables. Any y's are going to be considered constants. Let's go ahead and define a partial derivative, and then we'll try an example. So let's just take the notation for any function of several variables. So if z equals f of xy, right, we're just saying we have a function of several variables here, then the partial derivative of f with respect to x, that is, as x changes, x is the one we're thinking about changing here, and seeing the corresponding change in the function f. Okay, so we denote this using one of a few notations. I can use that subscript notation like I did before. I take the name of the function and I say who is changing? It's the x that's changing here. And then I use the function notation like that. Or it's perfectly okay to drop the function notation and just write like that, f sub x, and that's how we read that as f sub x. Or we can also make a modification on that d dx notation that we've used before. I can't use the d's though, because those are specifically for derivatives of a function of a single variable, and we're now in several variable land. Okay, so we modified that d dx notation a little bit, and we use little rounds instead of d's. We use little curled d's. So it looks something like this. You start by going like that, and you would say dz, because that's the output, over round x, right? So round z, round x. That's how we read that. Okay? And all three of these are equivalent notations for saying the partial derivative of f where x is being considered the variable. Okay? And how do we find all of these? They're the same thing. All we do is think of x as the variable, and we think of y as a constant. When we're differentiating. So we take derivatives as we usually do. All of our rules apply like we've had before. But when we're taking these partial derivatives, this is just one kind, f sub x, we have to think of x as the variable and y as a constant. And we'll do an example in just a second. We need to define one more partial derivative because there are two independent variables. And so if we have a partial derivative with respect to x, well, then we have a partial derivative with respect to y as well. Okay? So all we need to do is change a little bit of this definition, and then we'll have a definition for the partial derivative with respect to y instead. And the few things we're going to change are right here. This x is going to be changed to a y. This f sub x right here is going to be changed to a y, because now we're thinking about y as being the thing that's changing. This is just like before, where we said, okay, let's think about product B changing by 1 unit, and how much will the cost change by. That's what we're thinking about here. The y, or the second variable, is the thing changing. So we think of y as the variable here, and we think of x as a constant when we're differentiating. So the things I changed are right here. Let's go ahead and consider an example. If you're still writing, remember you can pause the video and back up if you need to. The notation takes a little bit to get used to, and the process. But remember, we just have to keep in mind who is the variable and who is the constant. So the example we're going to consider looks something like this. So we have a function, z equals f of xy, and it's defined by 2x squared minus 3x squared y plus 5y plus 1. And we'd like to find both the partial derivatives, meaning f sub x, the one as x is considered the variable, and we'd like to find f sub y, the one where y is considered the variable. Again, notice I've used that shortened notation where I didn't include the of xy notation, the function notation. Okay, well, let's first find f sub x. That's how we read this first one, f sub x. Okay. Remember, in this one, what we do is we consider x to be the variable, and any other letter, like y, for example, is considered a constant. So let's look at our function. I see I have 2x squared. Okay, x is the variable. 3x squared y. Okay, in this expression, the x is considered a variable, the y is considered just a number. Think of it like the number 5 or something. And then I have plus 5y. Aha, that whole term is a number because y is considered a constant here because we're doing f sub x. And of course, 1 is already a constant. So let's work term by term. The derivative of 2x, where x is a variable, is 4x. Derivative of 2x squared is 4x. Let's move to the next term. Minus 3 is a constant, y is a constant, and x squared is the variable here. So I have, in terms of my derivative, it's going to be 3 times the derivative of 2x, and y is a number, right? So 3 times, what's the derivative of x squared? It's 2x. And then we have just a y there because it's a number. It's sticking around for the same reason that the 3 is sticking around. They are the same kind of thing for right now, right? They're both considered constants, 3 and y. Okay. Next term, derivative of 5y is 0 because y is a number, and derivative of 1 is 0. Okay, so simplifying here, I get 4x minus 6xy. And that's our first partial derivative, okay, with respect to x. Let's do the same thing with respect to y. Now, who is considered the variable? The notation is telling us that y is considered the variable. Any x's you see in that function up there, in the function f, those are all considered numbers. Okay, so let's work term by term. What is the derivative of 2x squared when y is the variable and x is a number? Well, that means this whole thing is just a number. So its derivative is 0. There are no y's in that expression. That whole first term just says number. What about the next term? 3 is a number. X squared is a number because x is being considered a constant. Y is the variable. And y is the variable. So what is the derivative when it says number times y? It's the first. The derivative would just be the number in front of it. So the derivative here is minus 3x squared. Okay. Again, because this says number times y to the first. And the derivative of number times y to the first is just the number in front. Same thing here. The derivative of 5y is 5. Notice we just used the same logic between these two terms here. It says number times y, number times y. The derivative should be 3x squared, 5. And the derivative of 1 is 0. So f sub y here is negative 3x squared plus 5. We can actually evaluate partial derivatives here. I just need to be told where I'd like to evaluate them at. So I could, for example, say something like, what is f sub x at the point 1, 2? And I could use my function notation there then to write something like this. So hopefully you have f sub y. So here, I'll write it down here. What if I wanted to do the following? If I have 4x minus 6xy, I could then find f sub x when I plug in the point 1, 2. This would say to find the partial derivative with respect to x and then evaluate it at the ordered pair 1, 2, meaning when x is 1 and y is 2. So when I do that, I replace x with 1, y with 2 in the expression I have here. So I get 4 times 1 minus 6 times 1 times 2, which is 4 minus, well, negative 8. You see that? Oh, I went off the board. There, great. So we could do the same thing with f sub y. We could find out what is the value of this function, f sub y, what's the value of the derivative at the point 1, 2. And I just have to take the name I have for the partial derivative with respect to y, plug in 1 for x, 2 for y, so I get negative 3 times 1 squared plus 5, which is negative 3 plus 5, which is 2. Well, there's a couple of important applications that we'd like to see with these partial derivatives. If you'd like to see another example of calculating these partial derivatives here, you can look at example matched problem 3 in your textbook, which is on page 809, or example 3. That'll be another example for you to see more calculations of these partial derivatives. I did want to talk about a couple of specific partial derivatives, especially with reference to that special production function we have, which is the Cobb-Douglas production function. Which, remember, is a function of several variables, and it looks something like this. And remember, the important piece about this function is that m and n have to add up to 1. Okay. Well, since this is a function of several variables, we can think about its derivatives. So we can think about its partial derivatives in this way. And each of those partial derivatives have meaning, and they have a special name, because this production function represents an application. Remember, this is the output of this function is the number of products produced when x is the number of units of labor and y is the number of units of capital. So let's write just what those variables represent, where m is this and x equals number units labor, y equals number units capital. Okay. So let's think about what the partial derivatives would be. The notation would be like this, f sub x here. And what would this represent? This would represent thinking about how f changes or production changes as x changes, right? As the number of units of labor change. Wait, did we get those backwards? Nope, I think we have them just fine. So how do we think about this one? We think about f here as being production. So how does production change? This notation says, how does production change as the number of units of labor change? Okay, well, this is what's called the marginal productivity of labor. And I'll refer you to an example in just a moment, but I want to talk about the other partial derivative, which is the one with respect to capital. Just a change of notation here will give me the other one. If I change this to f sub y here, then I'm no longer talking about the marginal productivity of labor, because labor was the x variable. This is now the marginal productivity of capital. Okay? And this is really saying what? Just like we did with the labor one. If you were to increase capital by 1 unit, whatever the number is for this, it would be how productivity or production would change for that 1 unit of increasing capital. Okay, the f sub x one would have been for 1 unit of increase of labor, how production would have changed, right? So really it's emphasizing here what kind of power the capital and the labor have in terms of production, right? How are they directly affecting productivity here? Okay. So to see an example of this, and we'll talk about one specifically tomorrow, more in depth, read the next example, which is example number 4. And of course, you can pause the video, do that, and then come back. But the last thing we wanted to talk about in our video is the fact that not only do we have first derivatives, but we actually have second derivatives as well, just like we do with functions of a single variable. So we have what are called second order partial derivatives. And with functions of a single variable, remember, we just make use of that double tick notation to denote the second derivative, right? You would see something like this, f double prime of x or something, right? Again, we can't use the tick notation because we have more than one independent variable now, right? So far we've had to use something like this, right? F sub x of xy or f sub y of xy, right? So these are what are called the first order or first partial derivatives here, right? These are the first partial derivatives. Okay, and remember we find a second derivative, just in general, we find a second derivative by taking a derivative of the derivative, right? So we have to start out with a first derivative and then take its derivative to get it to a second derivative. Okay, well that presents a little bit of difficulty here because we have two first derivatives. So how do we find a second derivative if we have two of these ones? Right? Well, let's just start with one of them and see if we can get it. So let's start with this first one here. Okay? And let's see if we can arrive at what's called a second derivative, second partial derivative here. So let's say we started out with this first derivative, f sub x here. We took the derivative with respect to x. All right, to get a second derivative, we have to take its derivative. Well, there's two choices, right? We have x or y. Which derivative do we want to take? Well, there's two options then, right? So we have more than just a couple of second order partial derivatives here. We're going to end up with quite a few. Okay, so the notation we're going to arrive at here for our second order partial derivatives, we'll denote this sort of here, right? This is where they're going to go. If I say I have f sub x, that's my first derivative, right? Let me write the little x a little lower. If I have my first derivative here, I want to take its derivative. Well, let's say you wanted to take its derivative again with respect to x. You would do another little x to say you're doing the second derivative also with respect to x. What we could have done, instead of again with respect to x, we could have done with respect to y instead. So we start out with f sub x, because that's what we're starting out with for our first derivative. And instead of the second one being with respect to x, we say, nope, the second one is with respect to y. Okay? So we sort of stack up these derivative instructions here to say, do the first one with respect to x, then the second one with respect to x, or first one with respect to x, second one with respect to y. Good. And I think that exhausts all of our options there, right? If you start out with x, you can only do next x or y. You've got to pick one of those two. But remember, there's another first derivative here. We could have started out with y first. Okay. If we started out with y first and we want to take its derivative, we have two choices. So we could do x secondary, or we could start out with f sub y as our first derivative and take its derivative also with respect to y. So these four derivatives here make up what are called the second order partial derivatives. All four of these are all of the second derivatives of a function of two variables, f of x, y. So let's just see how this would work. Let's try calculating a second derivative. Okay. So let's try an example. Let me give you a function. I'm going to pick one from the textbook. All right, let's find f sub x, x, and that's how you read that, f sub x, x. The first thing we have to do is notice that it says to do the first derivative with respect to x, and then the second derivative also with respect to x. So the first thing we have to do is first find f sub x, the first derivative, before we find the second derivative. What is f sub x? It's the derivative of this expression where x is considered the variable, y is a number. So in this first term here, x to the third is the variable, y is a number. So the derivative here would be 3x squared, and the y is just a number. It's sticking around like a 5 would if it were in front. Okay. The second term doesn't have any x's in it, which means all of that is a number. which means its derivative is 0, and the last term is a number, its derivative is 0. So this is 3x squared y. Well, that's f sub x. I now want to take that expression and take its derivative with respect to x, f sub x, x. So now I look at this thing and I say, okay, where are there any x's, if there are any? I see I have an x squared here. So in this term, 3 is a number, y is a number, x squared is the variable. So the derivative will be 3 times the derivative of x squared is 2x, and the y is just a number. So this thing is what? 6xy. And this is what's called the second partial derivative, f sub xx. Let's mix it up a little. Let's find f sub xy. The first derivative is still going to be the same. F sub x is going to be the same exact thing. Okay? But now what is f sub y? What this means is that I now look at f sub x and I say take its derivative and think of y now as being the variable. So I look at this expression over here and I say, are there any y's in it? Yes, there are here, which means anything that is an x is a number. So everything, let's see, 3 is a number, x squared is a number, y is the variable. What's the derivative of number times y to the first? Well, it's just a number sitting in front of the y. Okay? And this is the derivative, second derivative, f sub x y, okay, which is 3x squared. Great. So let me refer you to example 5 as another example for you to read tomorrow. There will be some alternative notation in that example for the second derivatives, and we'll talk about that notation tomorrow when we're all together. It's just going to be a generalization of that round notation that I was using with the first partial derivative. They'll use it with the second partial derivative. Okay? So it may be beneficial to look at the box also on page 811. This example and the box are on the same page together. Okay? I'll see you tomorrow.